So welcome to the session. So this is Horizon 2020 Success Stories. Unfortunately, and no, you already know probably Cécile Huet, and you know it's not me. So I'm basically presenting in her behalf. Unfortunately, with the situation we have now, she was not allowed to come here, so she sent her most like big apologize, because she normally loves to be here in this robotics forum and be around. And my name is Marta Palau. I'm part of VU Robotics, and I will be leading the session, and we will have basically different projects that were funded, had been very successful, and now we will present here. So the main things they will speak about is like it's this uniqueness, why the difference they have made. Then also what has been the impact that the technology or any other of their activities they have been doing, and then also any results, and when they have collaborated with end users, some of them will also explain the cases through the end users. So we expect to see here quite a lot of nice stories and a lot of effort, because we know how much it takes to write a grant, get it funded, and that make it happen. And here are the 5 projects. I will not enter on them. I think I will leave that for our speakers. And I also invite our speakers to come here and present themselves, because I know some of you are also with other colleagues, so I don't want to have any problem on missing any name. So yeah, that's it. So I think we can start for the first project. It's robot arms, so idle arms.
Okay, so thank you, Marta, for the presentation. This is the first slide, and it's exactly the same slide that I put in the presentation of the project 4.5 years ago. So we wanted to have first aerial robots with multiple articulated arms on board and advanced manipulation capabilities, and we wanted to have also the application to inspection and maintenance. And I think that we can demonstrate that both objectives have been met. So just going to a little bit more the details. From the point of view of the new innovations, scientific and technological innovation, we wanted to have the first aerial robot with more than one arm, and particularly with 2 arms. And also we want to have the capabilities of the multi-directional platforms. And the second is that we want to have the application, not only in environment, control environment, but also in the real applications. So these are the objectives of the project. And I will try to summarize in these few minutes the results. So the first is that we think that we have very good research in terms of production, scientific and technological production. So we have the very first aerial manipulator with onboard capabilities for position and force control, visual servoing, multithrust. That means that we have embedded in the system, and also visual servoing without having markers with, let's say, general not conditioning environments. The second is that we have also onboard planning methods that take into account the characteristic of the platforms. That means that integration of the arm with the platform. So we plan trajectories taking into account this full model, and then we are aware of the characteristic of the dynamic, or in some cases aerodynamic characteristic of the platform. And then we published more than 125. This was at that time, that was August, by the end of the project. I think that we have much more now, which is not very common in many projects also, because we have in top robotic journals and conference. And we have this book, Aerial Manipulation, Robotic Manipulation book, that we produced with the partners in this project. So I think that also we have very important technological achievements in terms that we produced the first aerial robotic manipulators with multiple arms and fully autonomous multiple arms. There is some videos in which you can see some teleoperated system, but we have the first, and also with autonomy on board. And we have also the first contact inspection aerial robot. You will see later in the video. So we also developed one integrated system. So that means that the system that we integrate are able to have control, perception, and planning capabilities, all of them on board to perform the application. So we went to 2 different factories. One was a cement factory in Spain, and the other was a refinery in Germany. And then, and not only that, but we produce products that are very close industrial commercialization. So we have all these products in terms of something that can be marketed. And one company also was created, a new startup company that is summarized here. And then this is targeting the oil and gas sector, because it's also with the participation, strong participation of the companies that are in the sector already, so industrial inspection and maintenance. And the numbers are very good in terms of promising business for the next years. So I will try to show you a video, couple of minutes, 3 minutes video, summarizing the project. So we first developed compliance of the arm, which is very important in order to avoid the impact effect. But also we are able to land, this is CNRS, the previous one was University of Seville. They developed some technologies, as you can see here, also with multi-directional thrust and reliability. Also, you can see here the very first outdoor, it was also indoor, the first aerial visual surveying with all the capabilities on board without any marker, no marker at all. It's dual arm manipulation. So you can see here also how to exert forces to attach a sensor, first indoor. So this is the planning, and then we integrated everything in this platform that was able to build a map of the environment, to plan trajectories, everything in real time, and then to execute this planning in a complex scenario for an aerial system, just moving the arm at the same time that navigate inside these structures. And then we went to the industry. Well, first, this was another bigger platform with an industrial arm. We also wanted to show for the deployment of bigger robots. So this is for the deployment of a crawler on a pipe. The robot was the inspection robotic robot. And then we went to the factory, first to the cement factory. And then we built also the map, and we attached the sensor, so to work. And then it's a very interesting interface in which the operator just moved the end effector. It's a crawler with wheels. And then we went to the factory. And again, mapping of the factory, simultaneous localization and mapping without GPS. And then we produce the map, and then again we plan the trajectories, everything integrated, and then we perform the inspection. In that, the inspection was the wall thickness measurement, which is critical for the oil and gas. So you want to determine the wall thickness in pipes and also in tanks. And then the operator just move the end effector, and the platform adapt the motion fully autonomously. But the operator is required by the So we won the prize, the overall award of the European Commission between 25 finalists, and we won the award. This was the first time that a robotic project won this award. So we think that for all these reasons, our conclusions are So we combined technological excellence with high industrial relevance. So we think that we have not only this award, we have a number of awards of the individuals and group due to the achievement on the projects. So we think that thanks to the aero arms, right now Europe is in excellent position, I would say, in the leadership in the world of the aerial robotics manipulation and application to contact inspection. That's all. Thank you very much.
Thank you. All right, in my presentation, we're going to continue talking about robotic arms. Just in our case, they're not attached to flying platforms, but rather to human beings. I'm talking about prosthetics. In our project, which was called INPUT, which stands for Intuitive and Natural Prosthesis Utilization, we're trying to improve the interface between humans and prostheses and robotic arms. So my name is Sebastian, and I'm here and honored today to present the work of a much larger group, obviously. This picture was taken at our consortium meeting. We had also 3 amputees present, which were testing one of the first prototypes of our platform. So just a brief summary of the project. It was running for 4 years. It just ended in January of this year. It was a rather small project with 6 partners, but the key was that it was a very balanced consortium. So we had 2 academic partners, we had 2 clinical partners, and we had 2 entities of industrial partners. So that allowed us to spread all the research focus evenly over all the domains that we are currently interested in. So unfortunately, I'm not going to be able to talk too much about prosthetics per se, but there are just a couple of key factors that are important for you to know what is actually important for prosthetics and for a prosthesis to be successfully employed in a patient. So first of all, it has to be comfortable to wear. It's like a very expensive shoe. If you get blisters, you won't wear it, right? The same thing is with prosthetics. So you need a comfortable fit that is secure so you don't lose your prosthesis, and it doesn't give you any blisters either. Modern arm prostheses are controlled with muscle signals, so we obviously need an excellent interface between the muscles and the electrodes that pick up those signals. Furthermore, optimized control algorithms are important for ensuring good manipulation tasks with patients. Of course, you need a capable prosthesis, so I'm talking about pure electromechanical properties such as speed, torque of the fingers, etc. And last but not least, you need a well-trained patient. So a patient needs to undergo some rehabilitation and training in order to be able to use a prosthesis properly. Just as an expensive sports car, if you don't know how to use it, you're not going to do any fast laps. So you need some proper training. But once you achieve that, you can expect 2 results. The first one being clinical evidence, meaning showing that your system is better, at least in parts, than what we currently have as a state-of-the-art. And ultimately, that leads to successful translation into viable products and exploitation. So I'm going to show you some of those results that we achieved in the project. As I mentioned before, we had a very balanced consortium. So we had academic and industrial partners taking care of the signal acquisition and machine learning that we used for controlling the prosthesis. We had rather extensive clinical testing and evaluation with patients and also clinical training. And industrial partners were taking care of project management and also the exploitation of the results. So speaking of results, I want to present you the 3 main results that we achieved in the project. Obviously, there are much more, but just those are the most interesting ones, I believe. The first one is the Electrode Liner. Electrode Liner refers to technology which is similar to a sleeve or a sock that you might put on your arm. And that provides both the physical and electrical connection between the prosthetics and the residual limb of the amputee. So this is a very compliant mechanism. Here you can see that we stress tested it by elongating it, I think 100,000 cycles, which corresponds to the usual wear that you would expect from a prosthesis user to wear every day. It's made of polyurethane. It's very flexible, and it has those electrode pickup sites already integrated into the material. This leads to results that we get very good signal accuracy and signal quality, while also being very comfortable to wear. The classic standard prosthesis is made of a very hard material, and also it has to have holes for the electrodes to come through, so that's rather uncomfortable for the prosthesis wearer. The biggest challenge in this was the manufacturing process. So the prototypes we used during the project were mostly manufactured on a manual basis. But we recently partnered with another company called NTT, which is specialized in 3D printing of liquid wires. So that's exactly the technology that we need, some wires that are stretchable, bendable, and in additive manufacturing, technology is very quick to make. So this is one of the highlights of the project. Another one is the machine learning technology that we used. We had a partner, Ataxia, from Switzerland on board with Professor Schmidhuber, who is a very renowned individual in machine learning. So we had access to quite a large variety of machine learning techniques, in particular neural networks that we were using for achieving this task. And I'm not going to go through all of this list here, but we tried quite a few of different topologies and training methods for neural networks in order to get the best results. And ultimately, we were able to implement those on a commercial prosthetic controller. So this, you can see here the dimensions is rather small. It uses about 100 milliwatts of energy, so you can use it multiple days in a prosthesis. And as I said, this is a commercial prosthesis controller. But we were able to implement this neural network that came from our partner on this controller. Obviously, the training is done on a PC, but the execution and the control of the prosthesis is done online on a microcontroller. And that's very important for us because that means it will be easy for us to translate this result to a commercial product that is actually usable for a prosthetic wearer all day long. And lastly, we were developing a rehabilitation game. Serious gaming was a big topic of ours. We developed two different games. One is called the MyoBox game, which is a rather simple idea, but very effective for patients. Basically, the user controls a ball, and you have to go along those paths to collect boxes. And as you progress, the path gets smaller and smaller. So you need to be more and more accurate in how you control the ball, right? And the second game was a bit more advanced. So it uses the machine learning output, the regressor output, for controlling a virtual arm where you had to follow a beam of light and grasp some objects that were fragile or non-fragile, and so on and so forth. So the current state of the art until this was simple physiotherapy with a therapist, which is still very good, of course. But the problem is that patients usually have limited access to physiotherapy, and that depends largely on the healthcare system. So for example, in Europe, it's quite good. But in, for example, America, if you're not insured properly, you don't have access to such therapists. So such a game that you can just use at home for encouraging and training and improving the patient is very much needed. So these games, especially this game, was kept simplistic rather on purpose because it's very easy to implement that on a mobile app, for example. Currently, our controllers that I showed you before, they also have an app that connects via Bluetooth. So this is something that we can exploit rather easily as well. So in total, we tested our systems with more than 30 patients in a variety of ADL tests and standardized tests. So we had patients carrying suitcases around. We had manipulation tasks above and below waist level and so on and so forth, just to test the robustness of our system. Just to give you one of those clinical results, we investigated trunk and shoulder movement. So trunk movement being bending forward and shoulder movement obviously reaching. And generally what you can say is the less a person moves his trunk and shoulder, the better the prosthesis works, right? Because you don't have to compensate a lot for movement of your prosthesis. And that's what you can see in those plots here. In the first plots, you can see the pre-tests with users with their own prosthesis. And below here with the input system. And you can see that generally, without going into much detail, the area of the plots is much reduced, which means that they use less trunk flexion, they use less shoulder elevation in order to reach the same tasks and grasping objectives. So to summarize, the outcome of our project was that we have an improved human prosthesis interface, which means a better fit, it's more comfortable to wear and gives better signals. We have better control algorithms now in place than we had before, and we have better training of the patient, which is crucial for the success and acceptance of a prosthesis. And all of that is ready for exploitation. So currently, as you saw, for example, the Electrode Liner, we're going towards mass production, meaning that we do some of the stress testing that is necessary for ensuring the clinical lifetime, and also looking into manufacturing opportunities. The machine learning algorithm, as I mentioned, is already implemented on our microcontroller, so it's rather straightforward to just use that in a future product. And the patient training methods and games I mentioned as well are available and ready for use with patients. So with that, I would like to conclude my presentation. Thank you for your attention. And if you're happy, are there any questions? Please. Could you explain a bit more about this liquid wire? They're conductive, right? Yes. I think that's the number. Yeah, so you can see those liquid wires being here. In our first experiments, we tried extrusion of those wires. Basically, the whole matrix here is made of polyurethane, and these black wires are also polyurethane dotted with carbon, right? So that makes them conductive and still flexible. And so this liquid wire printing technology uses the same material, just that you get rid of the extrusion, which is rather non-consistent, I would say. And you can just simply print everything in one step rather than having layers and layers that you have of matrix, then wires, then electrodes, and then again the matrix, which makes it all in one step and easier. Right. Thank you.
Good morning, ladies and gentlemen. My name is Puya Mohammadi from Technical University of Braunschweig in Germany. It is my great pleasure to present a few of highlights of the EU project Cogimon, alongside with Professor Dr. Martin Giese from University Hospital of Tübingen. We had a consortium of 8 members, 8 teams from Germany, Italy, Switzerland, and United Kingdom, with different expertise in software, hardware, control, and also the human side of the stuff, the sensimotor rehabilitation. And with this strong consortium, what Cogimon tries to do was to understand better the nature of compliant and cognitive interaction in motion. So by doing that, we wanted to dig deeper into questions such as how a humanoid and a human can carry an object together, how multiple robots can cooperate with each other to do tasks that are otherwise beyond the capabilities of individual robots, how human can enter a contact situation, do a manipulation task, and go out smoothly, and how a humanoid can understand the intention of a robot, react accordingly, and of course the most important question for us was how can we bring this to the general public to be a benefit for them. So as you see, we had a strong focus on multi-robot paradigms, and we wanted to keep human always in the loop. To understand this question, to implement this application, our project developed its own software architecture, created new hardware, and of course, we advanced the control theory. Using these assets, we studied the human-robot, and robot-robot interactions, and perhaps more importantly, we also see how these fields and studies can contribute and learn impact from each other. For instance, we had some studies on the synchronization pattern that emerge when 2 people are walking hand in hand. So if they start out of sync, do their steps become synchronized? Do they go out of the sync? And it was very interesting for us to see the same situation that emerges when we have 2 humanoids carrying a tabletop, for example, with each other. So here the robots are mechanically linked to each other, but their software are not communicating. And we saw exactly the same situation. So even if the robots start out of the sync, slowly, the same synchronization patterns. This is, to the best of our knowledge, one of the few applications where 2 humanoids are doing this kind of tasks. Again, in the robot-robot cooperation, We did a lot of work in projected inverse dynamics. Here we have 4 robots carrying a lift which is beyond the payload of individual robots. And important application here is in industrial processes where the workers generally have to go under physical strain over long periods of time. By doing so, the robot would do the heavy lifting, so to speak, and then the human can do delicate manipulation tasks. So we never wanted to reinvent the wheel, but there were cases that our hardware was not sufficient. So on the right, you see the Coman by Italian Institute of Technology. They scale it up to Coman Plus. It's a robot more or less my height, a bit taller. It's a very, very capable robot. It has 29 degrees of freedom, +2 in hands. Each arm is redundant. It has a payload of more than 10 kilo, which makes it really, really nice to do object carrying. It also has a torque interface, allowing us to do this kind of intention detection that I mentioned earlier. So here the robot is following me, understanding what I want to do, go forward, go backward, and then perform suitable steps. This is a step toward assisted walking in relatively far future. Another part was that we created a new software architecture. It is open source. Our data sets are all open source as well. Please focus on GitHub. So our software architecture is transparent. That is, if you design something for your robot, you can test it on a simulator, and then seamlessly, without any programming effort, you deploy it on your real robot. We can even support transparent switching between multiple robots, because we don't deal with joints in this software system. We consider kinematic chains. So you say, I want to control the left arm rather than these 7 joints. It is also platform independent. So we have Oracos for our real-time computations. We have ROS for non-real-time, and we have a bunch of middlewares to communicate between the two. You would see in a second an important application of this real-time, non-real-time communication when Dr. Martin Giese would take over. We also created lots of domain-specific languages. So oftentimes we have this situation, you have a nice idea, you write it on a piece of paper, but then now you have to code. And roboticists are often very good robot programmers, but then there is a time constraint, other limitations. So what we did is that we created these domain-specific languages. What you can do, you can express your equations rather easily in block diagrams or even graphical languages. And then the code generator automatically converts it into a machine-understandable, well-structured software. So now we can have a look at an application of this software architecture.
Yeah, so one application in our project was a clinical one. This is basically treatment of patients or rehabilitation training for patients with cerebellar ataxia. So ataxia is caused by damage of the cerebellum and results in strong coordination deficits like you see in this movie. So people, for instance, cannot walk properly anymore. And we have found in earlier work that such patients basically benefit enormously. This video doesn't work. Benefit enormously from coordination training. For example, the task that we used here was a ball throwing task that was suitable to transfer it to a robot. We, as a first step, implemented the same task in a VR environment using the software framework that you have seen, providing feedback to the patient also by non-verbal cues. And this task is very nicely scalable to the difficulty levels of these ataxia patients, some of which cannot even stand alone. And in the second step, we then wanted to exploit humanoids to do the same task. What turned out to be problematic is that the compliant humanoids that were in the project were not yet robust enough for this type of evaluation. As an intermediate step, we therefore integrated the robot physics simulator in a full VR environment. And for this, it was absolutely crucial to have this cool software framework that Pooja just described, because this could be done very quickly. And this allowed us then finally to really do experiments with ataxia patients, optimize the system based on their feedback. So we found that these patients can deal even with the full robot physics in an efficient way. We also got very positive feedback from the patients and also from the physiotherapists.
Some highlights of our dissemination activities. We had more than 170 papers and still counting. We have several in the pipeline. We are hoping for 180. So these are in highly respected journals and conferences: Nature, Robotic and Automation, and International Journal of Robotic Research, etc. We also had several Best Paper Awards as well as other awards. We were the KUKA Innovation Award finalists, and I just realized that we may won a Best Thesis Award. We will see about it tonight. Nadia was nominated for that. We had a booth in ICRA 2019 in Montreal. We showed our project as well as the new robot Coman Plus. It was one of the highlights there. It was appeared in Reuters and other local media in Montreal. In general, we try to be in touch with the media. We had couple of articles in Cordis, as well as a relatively strong presence in the local and national media. So our physiotherapy stuff was very interesting for the press. One final note, for us, it's work in progress. So we just started 2 companies that are leveraging the outcome of this project in different fields. The physiotherapeutic juggling that you just saw is being added to the repertoire of the trainings in the University Hospital of Tübingen. And we have already one project as a ITP in Robmosis. We want to bring our software architecture to the Robmosis ecosystem to make it compliant with their stuff. And last but not least, we are working on a new EU proposal toward rehabilitation application. We are very keen on this. We believe it's a very, very important topic right now. Many countries in Europe, around the world, are facing aging problems. And we really like to continue what we have started. And with that said, on behalf of our fantastic consortium, I would like to thank you very much.
Good morning, ladies and gentlemen. My name is Werner Friedl, and I present SOMA. It's a pleasure for me to be here because our coordinator, Oliver Brock, cannot come to this event. And the main idea behind SOMA was to use soft robotics, as you can use in soft hands, together with environment constraints exploration. And we hope with this we are able then to solve in the future mainly 2 tasks. The one task is the Ocado use case, where we can use the hands to grasp delicious objects as groceries. And the other thing is to use the hands in social, interactive, human-robot interaction, as we can see in the Disney use case. And Lisa from Ocado will later present the results from Ocado. And we started to look on the human inside, how humans use environment constraints exploration. And we did a lot of experiments, and we can see humans use mainly, if you grasp objects from the table, 2 environment constraint strategies. The one is flipping the object. This you use for coins or credit cards, or you use the edge grasp. I can demonstrate it with my handy here. So it's the easy thing to slide the object to the edge, and then I can grasp it easily with one hand, or the other thing is the flip. And we developed also automatic labeling for this kind of task to analyze hours of videos and then use this later for the robots. And we looked also if we gave humans the simple soft robotic hands, what they can do with this if they use the environment constraints and also the hand wrist coordination. And this allows the human to grasp bigger objects than it would be possible with a top grasp. And we started in the project with 3 different solutions of soft hands. So we have the IIT Pisa hand, the DLR Avivi hand, and the RBO hand from TUB, and developed them further to the different projects. As we can see, we increased the numbers of freedoms in the hand, where the hands are used in both use cases, and we have the specialized gripper hand from DLR, the clash hand, which is more optimized for the Ocado use case. And this specialization we can also see in the soft surfaces we have on the hand. For the handshaking in the Disney use case, you need a soft glove, but on the other hand, for the Ocado use case, you want only partly soft surfaces to slip between the objects. And what is now the right softness for this hand? So we looked again at the humans and see that humans can vary the variable, the stiffness of their hand. And we built this grip perturbator where we can measure the Cartesian stiffness of the human finger depending on the co-contraction of their muscles. And we also measure the EMG signals of the intrinsic muscles, as you can see in the picture. And this we want to bring them to the robot hand, and IIT measure the grip stiffness to see if it's helping to avoid slippage on the hand. And this leads then to new variable stiffness actuators. As you can see, the TUB fingers can jam a layer and then change the stiffness. The IIT co-gripper can change the passive elastic elements and then change the behavior of the closing. And DLR improves the variable stiffness concept for N+1 design and differential fingers. And this is then used in the environment exploration. As we can see, it makes it much simpler if you can use environment constraints exploration. So you now can use the wall to rotate objects like books or form the simple hand by the environment to grasp only one book. Or use the hand to minimize the degrees of freedom of the object to grasp it simpler. And this can be also seen that environment constraints exploration reduce motion and perception uncertainty and leads to a simpler planning thing. To improve the thing, we also included feedback in our hands. As you can see, the soft glove for the Pisa soft hand, which tactile sensors can help to make a better handshake, or the IMU glove from the Pisa soft hand allows to reactive planning strategies, as we can see also here in the video. The hand is now detecting the object as environment, and this helps to grasp more complicated objects, very sensitive and better than with only force torque sensors of the cobot. And last not least, we developed 3 different benchmarks, and Lisa will talk later about the grasp performance benchmarks. And I will only talk about the hand and grasp resilient benchmarks, where we stress the single fingers by a pendulum or stress the grasped object by the pendulum. And you can see it here in the video. The thumb is crashed by this pendulum, and the variable stiffness actuation helps that the finger can sidestep from the collision. And this you can see also for the RBO finger. And here you see a crash on an object, and still the compliance help that the object stays in the hand. And in the future, this could help that your planner must not be anymore so accurate, and you can faster grasp object and deliver them. And now I go to the Disney use case. And the main idea was to use soft robots as a medium for social human-robot interaction. And Disney was not only interested to get a functional prototype, but the main interest was to understand the perceptive interaction quality. And we have two interactions here. The one is the handshaking, and the other one is the bidirectional handover between human and robot. And to start with the handshaking, we analyzed in a quasi-static benchmark how the hand contact location looks in the human-human baseline, and then compare this with the robot. And this leads then to improved robot hands. And then we developed different closed-loop controllers for hand control. And the hypothesis was that if you do consensus behavior between the handshaking partners, you can improve the perceptive quality. And this is true, and we found it out. And here you can see the demonstrator, where we can change the Cartesian stiffness of the grasping, and also the synchronized behavior of the motion. And last not least, we see here the demonstrator for the human-robot handover. And you can see this works very fast and reliably. And the soft hand allows to grasp very robust the object, what leads to exceed human-human interaction speed. And we will see it perhaps in the future in the theme parks of Disney. And now I give over to Lizzie.
Yeah, thank you very. Ooh. Okay, not a good start. So yeah, I just wanted to talk a little bit about more Ocado use case of in summer project. So my name is Elisaveta Konstantinova. So I joined this project quite late, but I will give you the insights of Ocado. So first of all, just a little introduction to who we are and what do we do here. So Ocado is working on innovation and modern technologies, including robotics, providing robotic solutions and end-to-end solutions for world-leading retailers. So just to explain the way we operate our retail part of a business. So the conventional way includes when you go to the shop, you have a delivery vans going to the shop from warehouses, and then you come to the shop and buy your products and bring them home. So Ocado doesn't have this in the middle, so you directly order online, and this comes directly to your kitchen, to the fridge. So this is our own robotic solution for automated warehouses. So here you can see the video of the robots in one of our warehouses that are hovering over a three-dimensional grid and picking up the products to compose customer orders. So at the moment we're planning to build over 40 warehouses all over the world, and are providing these solutions for world-leading retailers. So this is one part of our background, and another part is that we have more than 55,000 different units, different products that we want to pick and pack. So, and this poses a great challenge for us to manipulate different types of objects. So currently these solutions, what you can see here is a suction cup solution, and we're already operating it in our warehouses. However, as you know, not every object has a nice flat surface. Not every object is easy to pick with a suction cup. So that's why we're very interested in, particularly in summer project, and to understand what would be the best way to grasp more fragile objects such as fruits, vegetables. So what would be our best solution for that? So here you can see the packed produce in the Ocado warehouse. And so we specifically focused on challenges in grasping fruits and vegetables. So Ocado's contribution was not only the unique use case of a real retailer, but also the evaluation and benchmarking of different hands, as you just seen, for summer project. And we have worked on several benchmarking frameworks. So our target was really to access the robustness, reliability, and operational speed of robotic pick and place. So we have used different complexities of the arrangement of picking, starting from single objects in the tote. Tote is a storage box, to more complex solutions when we have layers of objects. And here you can see a video how we are grasping 3D printed mangoes. So we didn't use real products, we have 3D printed everything so that we can evaluate the performance of the hands multiple times under the same conditions. And here you can see how we're exploiting nicely the environmental constraints using the side of a storage box and then selecting the best picks. So this brought for us a great value and understanding. So just as an example, and to give you the kind of a volume of that and the impact of that on Arcada. So robotics research group started with only 3 people before summer project. So now we are more than 20 people and expanding more and more. So this means that we're able to demonstrate to our business the value of robotics and the value of grasping in particular. So in here you can see how the hand is trying to go in different orientations and eventually picks the fruit using the wall of the tote, of the storage box. Right, so, and as I said before, for us it's not only a research exercise, not only interesting in project, but also a big value for the whole business. So we can test which solutions are economically feasible, what we can introduce to our warehouses. We can understand where we stand in respect to competition. So we can select the best hands, we can select the best solutions, best approaches. Let's see the value of soft robotics, for example. And then, of course, we also, because we're expanding, we're working with different research organizations. So this means we can see which parties are worth collaborating with and with whom it's good to continue future relationships. And of course, this helps us to bring a better quality of service and also open new research directions within our research group. So this is kind of our perspective of not only as a research organization, but also perspective of a business who needs the solutions for practical applications and who needs to introduce the developed research in practice and make it work for people. Yeah, so this is my overview, and I have to show the slide that we are hiring, and please talk to me if you have any good candidates in mind. And here is some legal wording. And yeah, these are all the amazing partners that contributed to this project. And of course, thank you to coordinator Oliver Brock who made it all happen. Yeah. If you have
Okay, so my name is Paolo Dario. I've been the coordinator of the ENDU project. ENDU project is, like many of our projects, is about a dream. Because, of course, we are dreaming about the future and about great adventures, if you will. And as we know, great adventures have many heroes. I mean, people who have played a role in this field. That is about developing a solution for colon cancer. And those are the figures. So we were just 6 partners, 2 engineering teams, 2 medical teams, and 2 small industries. And it was a very, very nice consortium. At the end of the project, we had got the evaluation of excellent. What's the problem? You know, the problem is that colon cancer is not as well known as, for example, breast cancer or lung cancer. But in reality, as you see here, has a high incidence and, above all, high mortality. So the medical need is really very strong. Actually, this is like a plague. What is important is that, and this is true for all of us, so people like me who are older than 50, but also many of you or your parents, is really something that is extremely serious. And the fact is that actually colon cancer could be cured easily or quite easily if detected early. like for example, today is between stage 2 and stage 3, so with a relatively high mortality, that's the point. If we would be able to go to both stage 2 or even, like we want to do with ENDO, before cancer is originated. And you know, cancer, we know, is originated through polyps. And when we made like a fecal blood test, please, like me, don't be safe, because when blood is detected, actually we are already in this area. So what we want to do is to go here, when the cancer is not yet formed, and 100% of the people can be saved. So it's a big battle of which many people are not totally aware. Today, there is a gold standard that is colonoscopy. Those of us who have made colonoscopy know that while it is effective, it's not certainly a pleasant experience. And so many people are reluctant, simply reluctant to take a life-saving procedure like a colonoscopy. So what we want to do is essentially to have the same performance as colonoscopy. Please, I repeat, the same performance as existing colonoscopy system, but in a painful procedure. And this is the challenge. So you see, this is conventional colonoscopy. As you see, what happens is that the doctor, even the smart one, is stretching our colon, so creating, also insufflating air, any kind of actions that make the procedure not so pleasant. So those are the dreams, so the vision and the dream of the ENDO project, to essentially eradicate the colon cancer, and this is what I said at the beginning, before cancer is formed. So very early detection, and this is possible. For example, women, who are much better and smarter than male, they used to have breast cancer screening, cervical cancer screening with 80%, while today colon cancer screening is less than 20%, even in the most advanced countries. So we want to make this procedure painless and painless and effective and safe, of course. Okay, and so. This is our system. The system that we have developed is based on a disposable, also the disposable choice is very important. For example, an hospital in Germany was closed for 6 months because of bacterial infection, if you will. So in Germany, 6 months, a colonoscopy department is in Wolfsburg, I think, quite famous. So this is the concept that we are developing. So a capsule that is moved by magnets inside the capsule itself and teleoperated by the doctor. So it's a completely different procedure, if you will, teleoperated like in the Da Vinci system. And this is the platform. So we have developed all this. So just to say that in the project we have developed everything. You see the work that we have done, the capsule, and in fact with the final design very close to the possibility of application. And we have a number of deep innovations, okay? Disruptive innovations, if we will. The first is a very accurate real-time localization strategy for the capsule. That is very important. The second is advanced technology for human-robot interaction that makes, is based on collaborative technologies, but also advanced human-robot interfaces, you know, all things that are being very well designed. This is a unique asset. We have developed in Europe the best optical module in the world that has performance actually better than the best endoscopic system produced in Japan. It's another very, very unique asset that we have. Also, we have 3D reconstruction, automatic polyp detection using AI techniques, also deep learning, if you will, to identify with very high accuracy the polyps, okay, which are the real enemies that we want to identify. And we made a very important test, not only in vivo, not in animals, because in Europe this is almost forbidden, and this is good, because we have developed one of the most advanced simulators for making tests with the same or even better, I would say, results than animals, okay? And not yet in humans, but we are close to. And what is interesting, by the way, is an observation that we suspected. In this technology, like in Da Vinci, young doctors are better than old doctors. Very interesting, you know. It shows that this kind of technology, in fact, of new techniques can be better learned by fresh, even non-expert, but familiar with robots doctor than older doctors. Of course, we have made a lot of dissemination papers and so on. But the real challenge, you know, I'm an engineer, so to me, success stories are not only publishing good papers. Of course, I'm very interested in good papers, but my real challenge is to overcome the valley of death, okay? And unfortunately, we are still in the TRL level, or actually we were at the tier level between 4 and 5, and at the end of the new project, we are between 6 and 7. Okay? So we have almost overcome the valley of death, okay? But just, you know, to be there, you see all our effort that have been done systematically, including the submission to the ethical committee, we are not yet there. So what's next? After that, we have gone from TRL 4, 5, 6 to 6, 7. Sorry. The next is to exploit. So one of the partners has been appointed as responsible for industrialization clinical test. It's a spin-off company of the Scuola Superiore Sant'Anna, our university. And here is what Mediate is doing. So you see essentially, you see here the list of the analysis, the business plan we have done, and we are aggressively looking for venture capital. We have been unsuccessful yet, even if we are in touch with 2 of such funders who are very interested. We have also thought international, immediately. Actually, China is the largest market in the world. And so we have created a joint venture with Chinese universities because we don't want to produce our devices there at low cost and import in Europe. The contrary, we want to export by making a joint venture in China, European product directly. So at the same time, while we are looking at the European market, we are also looking at the global market. And that's it. Thank you for your attention.
Okay, so I'm here to present the project Robotnet. And you can see we were only 4 partners in the project. It was coordinated by me from DTI. Then we had Tecnalia in Spain, MTC in the UK, and Fraunhofer IPA in Stuttgart in Germany. And the project was really about how can we make sure that all the good technology that we develop in, for example, the European project, that we make sure that they cross this valley of death that Paolo just mentioned as well. How can we make sure that the technology we have somehow find its way all the way into the marketplace, which is somehow the reason that we're all working on these topics. So it was really a lot about how can we make the technology transfer going from research project and out into the companies. So this was somehow the whole purpose of the project, and this is from the initial statement also in the proposal we made 5 years ago. So it's really about how we make sure that these products come out into the industry, both in industrial settings, but also in service robotics and in all other domains. And the model we used in the project was this one. So it was really about to make sure that we could interact with a lot of companies out there, instead of only seeing from our side and come up with the good ideas on what robotics could be used for. We wanted to ask the companies. So we asked a lot of companies and invited them to come with the ideas, both robot companies or robotics companies, but also from the end user side. So actually during the project we had more than 200 companies coming to us and telling about ideas for robotics, both because they already had a robotic product which they want to further develop into a new application, but also end users looking for technology which they couldn't find in the market already. So based on that, we squeezed it down and choose 62 of those, where we had the opportunity to spend 3 person months in the consortium to really look a bit further into the potential, both on the technology side, but also on the market side, the business side, the implementation side. Could this actually become a feasible solution which could become a product, which somehow could also be scaled and become a good business afterwards for a robotics company or a group of companies? Based on these 62, we choose the 8 best of those, which we could take even further and to a high TRL, where we had a final demonstrator of the product that we were trying to target. So it's really trying to take this to a number of gates and make sure that the one we selected was the one with the biggest potential. So you could say somehow pick the winners in these ideas that we got. So that was somehow the main activity that we had in the project. Along that, we had a lot of training activities, a lot of open labs, we did a lot of videos, so there's a lot of dissemination in this as well. So we really want to use this as a way to get companies applying for this and become part of the project. So again, to get the best ideas, we want to make sure that as many companies as possible have heard about the option in the project like this. So a lot of dissemination on that. So just to show a few of these 62, so what you can really see from these pictures is that we've been out quite broad in different domains. So of course we've been doing something in manufacturing, but we've also been looking outdoor robotics, last mile delivery, inspection in construction industry and so forth. So really a broad domain. And it was really, from the project side, we didn't have any focus. The focus was really that we wanted to select cases where the TRL level was so high that we could, within the project, we could make sure that we could actually take it so close to market as possible to make sure that we could have a plan afterwards to take it for commercialization. So this was just a few of the projects that we did. Out of these 62, as I mentioned, we selected 8, which we call pilots. And that was really to take it to a TL7 demonstrator, which was the furthest we could go in this scheme that we had. One of the important things is that the pilot was not really just about technology. Of course, there was a lot of technology development and integration and putting together a lot of these technologies to do the system and the application. But it was really also about making sure we had the roadmap. Because as we all know, at some point the project will end. And that's where you maybe have the most difficult barrier somehow. How do you go from TL7 to TL9 and make the product go into the market? So we also wanted to have a plan for what would be the next step, who are going to do what. But because you could say in this transition, we have the companies coming in with the use cases and the problems. Here there's a lot of work from the partners on maturing this technology and finding out what should happen. And of course we were also heavily involved in this place, in this phase of the product, where we also involved a number of companies. But somehow, at some point, the partners need to withdraw and need to be taken over from the company side. So we wanted to have a clear plan on who were going to do what, who was going to be the exploitation partner, which of the companies going in here and become part of the pilot would actually be the one taking it into market and so forth. So that was somehow very focused on that. I brought a couple of videos showing what a pilot was. So the first one is this one called Gasbot.
We wanted to find a way to reduce the painfulness of the cylinder handling and transportation. This project allowed us to integrate technologies in an innovative prototype dedicated to cylinder handling. This project allowed us to break technological limitations of this kind of products.
So this is one out of the 8 pilots that we did. And you can see here it's really about that we have the French company Eradicate coming in. They have the problem. They want to remove these gas bottles. And we try to set up the consortium and finding out who could be the right companies also to to develop these kind of solution and find out how good it could look. And the interesting part is, of course, that some of the things we looked into as well was, of course, the potential at Air Liquide. Air Liquide is a very large company, so they have a huge potential in their own sites on using these kind of technologies. But of course, it could also be used in other domains, because there's a lot of handling out there and a lot of logistics still not automated. So the technology and the product foreseen here can also be used for different products out there. So again, that was some of the things we looked into in the pilot. Could it actually scale afterwards? Would this be a dedicated application, or could we see a product which could be used in a multitude of applications? So one of the other cases we looked into was this one. So this is electronic. So of course there's a lot of automation already in electronic production. If you have high volume, it's already automated. But we also have a number of companies, especially smaller companies, who are doing electronics, and there's still a manual work, where you have a workplace like this, and people putting in the components and doing the soldering afterwards. So what we tried to do here was to look into what kind of technologies can we use to minimize the time we need to program this kind of setup. Because of course it's small volume, so it needs to be fast to program the robot to do that. So what we use here is really that you can see up here, we already have a digital model of the PCB. You just point out where you need to put in your components in this. Then it's fed into the system. We have a camera on top, which makes sure that it's completely aligned, so we know where the PCB is actually placed. The thing is, of course, also that the components we put in here have different sizes and shapes. So what we also developed was a new way of handling this component. Instead of changing the grippers, we made a system where we could change the fingers, so that the fingers are dedicated to the components we need to put into the PCB. And of course, we need to have a really solid and precise grip to be able to put it into the print afterwards. Then based on all this input that we have, we do some algorithms behind, and then the system will start putting in the components. What you can see here is, of course, also that even though we have all the models of the parts that we have, in reality there will be some, maybe a small disalignment on the components we need to put in. So we use force control to make sure that the components is actually going through the holes before we just push in and so forth. But the main thing here is really that we have a complete digital setup of the system. So the user only need to be involved in pointing out where the part should go in. The robot is programmed on the fly by this digital model and start the production, which means we can really set up a new system or a new component within a very short time. What we also looked into in these cases is really to say, okay, all companies have different electronic compositions, they have different products they want to do. So again, here we looked into how should it be delivered. There would be a lot of options for different companies. They need different fingers depending on the components. So also really looking into the whole value chain and finding out what option should there be, who should deliver it, what would the cost be. So really trying to look into it also from the customer side and finding out what is really the business case on that. And to make sure, because most of these companies would maybe have a return on investment for within 2 years or so, could we actually do that and so forth. So really having all these different setups in mind as well was an important part. This was the 6 other pilots that we did. I will not go into the details of each of those, but it's more to show you, again, that it's been a lot, both in industry, but also in other application, pest control, assembly, welding, and so forth. You are able to find all this material on the web page where you can go in and get a case study on what we did. We asked all the companies who participated in the project what they thought about it, and we're quite satisfied with the numbers that we got. So all the companies would like to participate in this in the future as well. So indeed we have a confirmation here that this is something that the market is really looking for and asking for. They would like more of these kind of projects. Also very good score on the satisfaction on the collaboration with the consortium. So of course we're really happy about that. So some final numbers here. So as you saw before, we had through the project we have had more than 200 business ideas we looked into. We developed on 60 of those to get a bit more information on if they were good or not. 8 of those was turned into TL7 installation, and we have a plan for going to market with the solutions. So you could say that what we really did is that we took a number of these technologies which have been developed, for example, in FP7 projects, but also national projects and so forth among the partners and in the community in general, and really matured that. So we have really increase the TL level on a number of technologies used in these pilots. Then we have had more than 4,500 people involved in the projects, training courses and open labs. So of course you saw the partner list in the pilots. We have all the companies going in with the 200 ideas and the vouchers and so forth. But also we hosted a number of these open labs. We did training courses, both on the technical side, but also on the business side. So we have had direct contact with more than 4,000 people in the project, which is quite a huge number. We produced a number of videos, both on the vouchers we did and of course also on the pilots. We had over 100,000 views on the videos, so you can go to our YouTube channel and see all the material there as well. Of course also on the webpage. More than 750,000 people have seen the material in general, both through the webpage dissemination we did, LinkedIn and Twitter. So again, quite a huge outreach activity. So it's really to make sure that the material that we did, the purpose is of course also to be an inspiration and to somehow get more companies into automation and robotics. So it's also really about to make sure that we have the knowledge out there so companies can go in and start their automation journey and start doing more about robotics, because of course there's still a huge potential in a number of domains on these kind of technologies. A huge part of this was also really how can we make sure that when we have these RTO institutes across Europe, how can we really work together? Because what we want to see is also that in these digital innovation hubs, that how can we use each other's facilities and competences to help our local companies. So that has been quite a huge success on how we could supplement each other in these projects. And what we actually also have seen is that not only the projects within the Robotnet has turned out, but we also got so far 30 new commercial projects among the partners based on which can be directly linked to the activities we did in the project. We also have 17 new public funded projects. So this has also been a way to really create a number of new projects. And of course some of these are come from that we had this selection procedure going from 62 to 8. We took the 8 best. It didn't mean that maybe number 9 and 10 was not a good idea. It just meant that we didn't have the funding within this project to do something about it. So we also could took that into different scenarios and different funding opportunities. So what we really did here is that we have now a strong commitment and foundation between these RTOs to have joint collaboration across Europe, which somehow can facilitate that we have become fast in developing new robot solutions across Europe and helping the companies become more competitive in that sense. So that was some of the numbers in the project. And by that, I would like to thank you for your time.
Hello, everyone. I hope you're not sleeping, because I would like to ask you a question I was asked recently by some very important guy from a very important ministry of not quite important country, my home country. Why do you guys do robotics? Why not fintech? Why not insurtech? Whatever. And I thought, well, I'll do it because it's fun. But on a second thought, I thought, well, not only because of that. I don't care how bombastic it's going to sound. We do it because we do believe that with robotics we can empower people to do extraordinary things. For you and me, it would be maybe running a marathon or charity run. Anyone run it? It's too difficult, right? Or climbing a mountain, whatever. For Jan, he's one of our patients, reaching out for a bottle of water and some food is already too much. It's unreachable. So what we do, we try to empower people to reach the unreachable. And I know that many of you are driven by the same principle. That's why I'm proud to show you this. This is not really a success story, or it is, but not directly a success story of one EU project. It's a success story of many, and it's a very small success, I would say. We're not a big company with millions of funding and so on. We're a small company. But, and we were asked also to bring an end user with us, and no one brought an end user. We couldn't bring one too. Well, Jan is a tetraplegic. He cannot move his hands, he cannot move his legs. He lives in a wheelchair. But thanks to the arm we've developed, he is able to live an independent life. That's a big thing for him. And I was thinking about this end users, and I remember that Eric, the guy who is integrating these arms with wheelchairs of those kids, rang me one and said, you know what happened? One of our kids who doesn't speak almost at all, just gave him a ring, dialed his number on his phone or whatever he has, and Eric picked up the phone and heard just 2 words, Danke, Alter, which means thanks, buddy. He passed it to us, and I passed it to you, because this is small success of not only us, but this whole community. This whole grows on this community. So I thought, okay, what I'm going to tell you today. So I just thought that I will tell you where we are and how we got there. Maybe you will pick up something from there, maybe not. But just a few words about myself, not because it's my favorite subject, but it's somehow relevant to what we will do. During my PhD time, years ago, 15 years ago, we were doing teleoperation systems. I was building robots which you can touch. They were compliant. They had force sensors, everything. You have now in the robots, we were teleoperating those robots. We had some project with unscrewing explosives, so we were really proud of doing this. But it was a research project, also one of the EU-funded research projects. Then after my academic time, Lublin, Berlin, Munich, I went to the dark side and I worked to the industry. I worked for Airbus, Audi, some surgical company. And I also run the Acrea Engineering, which is does it work? Really? It's an R&D company. We build robots for research mostly, but also for industry. We do mechanical, electronics, engineering. We do prototyping. We have our own CNC machine. So it's been 15 years, and we're building basically all kinds of robots. These are some projects we're participating, and today I'm going to tell you about the 2 of these. One will be Remedy and one RAMSIP. So in Remedy projects, this is the teleoperation system before we did for Bundeswehr, for German army, but this is the same principle. So what we do here in this project, we want to handle the problem of doctors or expert doctors not wanting to move to the provincial areas. So anything else was almost already telemedicinized. You can do X-ray, you can do teleconsulting, but you cannot do ultrasound. You cannot do ultrasound. So we thought we split this situation into the patient side and the robot side, patient side and robot side. And the doctor, sitting in some expert hospital, is controlling the robot with bilateral teleoperation. I will not go into the details, but we have. So that's our robot. We built it. There was you could talk to each other. There was an arm holding an ultrasound probe with haptic interface, with force feedback. So you would have the 3D video channel, you would have the ultrasound channel, you would have the teleoperation, teleconferencing channel, and we did it. These are the experiments we run over distance of 500 kilometers. And then we looked how we can commercialize it, and this is not a very successful story, but you can also learn from not successful stories. If someone interested, please contact me. And this is another one. This is a project we've done together with Dimitri, Satoshi, Zoe. She was somewhere here. Very noble consortium. Again, thank you very much. And the project was devoted, there were several other partners as well, devoted to a robotic caregiver of a person with dementia. So, and a number of functionalities, cognitive support, monitoring, physical support, reaching up to the shelf for medicine, reaching down for a fallen object, cognitive stimulation. We've built a few prototypes of this robot, and since we're in Spain, there is this nice video showing the several use cases, fall detection, turning off the cooker, turning on the light, of trials we performed, or our partners performed in Barcelona in private flats of real patients. So the robot lived with the patient for a week with 12 different patients. So, and it was working and it was evaluated. Actually, right now we know what we really need in this robot and we don't. So we're ready to to make a really functional one. For this robot, we developed a range of drive modules, like any other, almost. They integrate the harmonic drive, the motor, the sensor, the electronics, also force sensor. We have like 6 or 7 sizes of this. So out of these modules plus some custom-made shells, you can build any robot, 2, 3, 6, 10 axes. And the shells can be from metal, from carbon fiber, they can be even 3D printed. So you can have basically any robot you want. Here are some embodiments of this. So you have some assistive arm, you have ultrasound arm, you have arm which we intend to be for biopsies and punctions, and the RAMSIP arm, which is now already on the robot. Somehow, we were with this robot on some exhibitions, and people, this is the real-world use case, people integrating these arms with wheelchairs came to us and asked, guys, can you make this arm for us? And they said, okay, this is ideally the RAMSIP arm. So we adjusted it for the use case. They said that they want this arm to enable eating and drinking, opening doors, controlling with wheelchair, joystick, basically no need for caregiver for the person. Okay, we said yes. And we made the first arm, first version of this arm. And to be honest, I didn't know that making an arm for a wheelchair is that challenging. It has to be safe, of course. It has to be low power because it's otherwise we drain the wheelchair battery. It has to be lightweight, and it has to have minimum footprint and volume. When not needed, it has to be folded under the arm support. They didn't like this arm because it was too big. It was 95 millimeters, and they said that's too much. So this is the second version of the arm. It's less than 5 kilograms. It's very small. It's very compact. It has unlimited John rotation. What can you see here? We are really proud of this arm, and we have it on a display down there. It's sensitive. It has force sensors, so you can remotely control it. You can program it for autonomous. You can have a physical contact with them. We have, as I said, torque and force sensors everywhere, and it's less than 5 kilograms. So it's made of carbon fiber, and yeah, we're proud of it. There is actually much more we can do with this. It is already, for someone who's interested, is a CE-marked, registered product, and it's been 1.5 years just to get this bloody CE. And this is supported by our national grant. We also have a very interesting gripper. Maybe we could pick fruits with it. Since November, it's on the market. We can do much more, so we have the whole palette of directions where we would like to go. I will not go into details, but just the 2 of them. Based on this arm, we are working on an assistive robot for minimum invasive surgery, the robot to hold the camera and the instrument. And also we're going to robotic needle positions for biopsies and ablation. Again, there are some advantages of this. That's basically it. I would like to thank you for helping us to reach the unreachable, just like Jan giving his father a high five for the first time. Thank you very much.
There's any questions? If not, I would like to thank a lot our speakers for this very inspiring and amazing project they have been doing, and also thank you to the audience that has come here today. So see you next year in ERF 2021 in Rotterdam with more new success stories, hopefully. So thank you very much. Bye.